This is problem 3-61. It's on page 111. Determine the height D of cable AB so that the force in cables AD and AC is 1/2 as great as the force in cable AB. What is the force in each cable for this case? The flower pot has a mass of 50 kilograms. So I'll show you the picture so you can see what we're dealing with. Because I'm not going to draw the whole thing at the board. I'll just draw a schematic of it, just a free body diagram schematic that is really three-dimensional, but I've only got a board in 2 dimensions here. So here's the point where the flower pot is connected, has a weight W. We'll figure out what that is, and generally we've got FAB in this direction, FAC, something like this, and FAD like this. Okay. Now I've rotated it slightly in the view that I've got versus what they have. But still, we've got an axis coming down, something like that. Okay. And the height we're interested in for FAB is a height D. I guess you could use lowercase d there. Okay. Because unfortunately, they've got a point D, capital D, and a height lowercase d. And of course, they've got a lot of geometry there as well. Now the constraint that they've given us is that half of FAB equals FAC, or in other words, the force in cable AC is half the force in AB. So this sort of Lone Ranger, if you will, by itself has twice the force of what AC has in it. Now referring back to the diagram I showed you, we can sum forces in the z direction. Obviously the weight acts downward opposite the positive z-axis, and there's a contribution from AC in the z direction, from AD in the z direction, and from AB in the z direction. But the sum comes out to 0. Now I went ahead and calculated the weight as mg, mass times acceleration of gravity, and so the mass was 50 kilograms times 9.81 meters per second squared. Plug it all into your calculator and you'll find the weight. I'm just going to erase this part. That comes out to about 490.5 newtons. Actually, not approximately, it comes out to exactly. Of course, the acceleration of gravity is not exactly 9.81, but for our purposes, that's close enough. So 490.5 newtons is weight W. Now, looking at each one of these components, FAC in the z direction would be FAC times what? What geometry would give me just the vertical component of FAC? Well, the direction is 3 up on the z-axis, and the length of the geometry representing FAC, or the direction of FAC, would be 6 squared plus 3 squared plus 2 squared. Okay. Now, if you think about this, you'll realize that FAC in the z direction has to be equal to FAD in the z direction. Why? Well, notice that AC and AD are laid out symmetrically. Okay. This FAB doesn't have a component in the y direction. So because of symmetricality, you'd realize that this is FAD in the z direction as well. It's supposed to be a capital D. There we go. Now this number, they've made it nice. 6 squared is 36, plus 9 would be what? 45, plus 2 squared is 49. Root of 49 is 7. So this is just 3/7 FAC, or also 3/7 FAD. Now FAB in the z direction, working on this term, that's going to be a little bit trickier because we've got this height, this unknown height D. And so we'd write the magnitude of the total force vector and then scaling it based on geometry. It's the vertical direction, so we're going to have just d over root d squared plus this length squared, which is 6 squared. Okay. Now, I don't know what D is yet. That's one of the things I want to find, but I know that this is true. So now, this sum of forces can be expanded just a little bit to actually write negative 490.5 newtons. I'll eliminate the, well, I guess I'll plug in the units, plus FACZ, but that's just 3/7 FAC, plus 3/7 for AD, FAD, plus, since I'm putting the scaling factor first, D over root D squared plus 6 squared FAB, and the sum still has to come out to 0. Now, since FAC and FAD are equal to one another, and they're also half of FAB, then look what we can do. We can write negative 490.5 newtons plus 3/7 plus 3/7. Notice I'm putting these together. 1/2 FAB plus D over root D squared plus 6 squared FAB. And look what we've got. We've got an equation with only FAB as the unknown. Okay, so if we move this to the other side, 490.5 newtons equals, now let's see, we have 6/7 divided by 2 is 3/7, so that's all of this mess, plus D over root D squared plus 6 squared times FAB. Okay, so that's helpful, but we don't know FAB and we don't know D. If we had either one, we could find the other. So I'll call this equation 1 and pause for a moment. I think we've used up F sub Z as much as we can. In fact, I don't really care about that sum anymore. What I care about is equation 1. That's what will be useful to me. So now I've got a relationship between D and FAB. Well, let's sum forces now in the horizontal direction, see what happens. Well, AB has a horizontal component. AC has a negative horizontal component. And AD has a negative horizontal component. Okay, remember, both these are back this way against the x-axis, whereas AB is in the positive. So anyway, this sum comes out to 0 because, of course, the weight has no component in the x direction. Now again, AC and AD are equal to one another, right, because they're symmetrical. And so we should be able to write from this, let's see, FABX equals these two on the other side, but they're equal, so 2 say ACX. Okay. Now FABX is FAB times what? Well, we just want this 6 meter length over the hypotenuse. 6 over root D squared plus 6 squared. On the other hand, for this side, FACX can be evaluated. Let's see, we only want the horizontal piece, so they go back 6 meters, or at least the scaling does, 6 over. It's going to end up being the length, the geometry length. We've already discovered this, the square root of 49, so that's 7. 6/7 of FAC. And so now we can take our sum of force equation and say FABX, which is FAB 6 root, or over root, D squared plus 6 squared, equals 2 times 6/7 FAC. But again, we know that FAC is half FAB. So look what happens. Those twos cancel nicely. The 6's cancel nicely. And we have another equation that relates FAB and D. Okay. Oh, by the way, Actually, FAB cancels, doesn't it? So what we've got then, the only thing that's left is 1 over d squared plus 6 squared equals 1 over 7. So in other words, the square root of d squared plus 6 squared equals 7. So if we square both sides, we'll find d squared plus 6 squared equals 7 squared. Well, 7 squared is 49, minus 6 squared is 36. And let's just write it out. So d squared equals 49 minus 36, just moving this 6 squared to the other side and taking the square. That number comes out to be 13. So in other words, d, this length d, is the square root of 13. And by the way, the units are feet, I believe. No, it can't be feet. We're in the metric system. These must be meters. Let's see. Looking at the figure, yeah, all the lengths are in meters. If you're curious what that number is, it's about 3.606 meters. Okay, so there's length D. Well, now that we've got length D, can we go back to equation 1 and say what is FAB? Sure. FAB is 490.5 newtons divided by all of this, right? 3/7 plus, now we know D is root 13 divided by square root of D is again root 13, so square it, you get 13 plus 36. And those are just numbers. You press all those buttons and plug it into your calculator and you'll find this is about 519.8 newtons. Notice that this is dimensionless because 3 meters over 7 meters, meters over meters cancel. Same thing here. You've got meters over meters. So we end up with simply newtons for FAB. Now one thing you might notice is we never summed forces in the y direction. Why? What would be trivial? Summing forces in the y direction, what would you have? Well, AD has a positive component in the y direction. AC has a negative component in the y direction, but we already know that AD and AC are equal. We know they're symmetrical. So while this is true, it doesn't really help us. I mean, I guess you could use it to prove that AC and AD are equal to one another, but that's pretty obvious from the symmetrical nature of the figure that was given. So what have we found? Determine the height D, we did that, check. What is the force in each cable for this case? Well, let's see, we found the force in AB. Finding the force in AC and AD then is trivial. It's just half of this, right? That's what, roughly 520, so 250, 260 or so. And I think I did that as well. Yeah, so if we take half of that, we find that it's about 259.9 newtons. And of course, that's the same thing as FAD, since AC and AD are equal to each other.